Hey, can y'all hear me? I just need a thumbs up. Let's see. Yes. All right, cool. All right, so just before we start, uh, people have been having problems accessing those lectures on the Zoom cloud for some reason, something regarding a password all the time. So what I've done is I've shared it in the pages tab. Like if you go to the Calc One lecture under the pages tab where I initially posted our first lecture, which brought you to a link from YouTube, I posted the links to the Zoom Cloud videos that we've done and their respective passwords right there. So I adjusted some setting on there that said remove the password, but for some reason it's still asking you guys for it. So again, if you just want to watch the videos, go to the pages tab on our course, the Calc One lectures, and everything's gonna be listed right there for you guys to access it. So now, reminder, y'all have y'all's first test right this Wednesday. It's an hour long, and basically you'll take it. It'll unlock from 4 o'clock to like 5:10. I say 5:10 just in case you come in a little late. But again, once you start it, you only have an hour, and it has to be finished by 5:10. So you can't come in at like 5:09 p.m. and then say, "Haha, I'm gonna have a whole hour." No, you will have 1 minute to take the test before it locks you out. Now, as far as scratch paper, it is allowed and everything like that. So, and let's say you can't fit your answer on the test. The test is just going to be under the quizzes tab, but many of them are multiple choice. Some may have an answer box, depending on what it is. If you can't fit your whole answer in the answer box, then what you got to do is take a picture of that particular problem right from your scratch work. Make sure you label the scratch work right. Like if you worked number 10, put number 10 on the paper and take a picture of it, and then just email it to me so that way I can see your work in that instance like that if you can't fit the answer on the answer box. But for this one right here, like I said before, I think there's 14 questions, 14 to 16 questions. Some are multiple choice, so it's just like looking at a graph, for example. So you're definitely going to have ample time to work out all these questions. And then at 5:15, we shall resume class, or we'll pick up with the Zoom stuff, and then we'll do one section and continue on with the course. Now, once you submit the test, it's gonna spit out your grade right then and there, and it'll tell you instantly what you made on it. So we only have one section left, and after this, I'll just throw up random problems that we can work out for practice. But make sure y'all work additional problems out, right? Don't think bare minimum. A lot of people like to think, what's the bare minimum I need to do so I can pass the test or do whatever. Don't think bare minimums ever. Just work more problems. It's always okay to do more, right? It's never okay to do less. So don't think, what's the least I got to do? No, it's okay to work more problems. Or if you're not confident in factoring, go factor more. If you're not comfortable with fractions, don't avoid them. You gotta know how to do them, right? So go practice it. Stuff that you're weak on, go practice it. Okay. If you need extra problems with something, Google it, right? Like say, I don't know how to add and subtract fractions with unlike denominators. What should I do? Go to Google and say how to add and subtract fractions with unlike denominators, and tons of stuff will pop up. Whatever topic you're weak on, like that, that's not calculus. You need to go. You can go on Google and just type in how to do it, or I need worksheets on it, and boom, it'll spit out tons of information for you. So, section 2.8. What is this? It is. I don't know if y'all looked at it before, but it is very similar. It's actually the exact same thing as 2.7. This is just called derivatives right here. And we talked about this last class. I said derivative is just a fancy word for instantaneous rate of change. So rate of change was like the slope, right? That's what we did in algebra, where you had 2 points. We had 2 points. If we had a curve, right? We looked at this from the last class, like we had 2 points, right? Like this was P and Q right here. And the slope, remember the slope basically gave us the rate of change, which is like rise over run, right? Rate of change between 2 points. B/T means between, right? 2 points. But derivative that means the instantaneous rate of change. So what was the difference between instantaneous rate of change and rate of change? Well, instant means how fast something is changing at one individual point, right? Because remember the last class when we talked about it, what do we basically do right here? We move this point Q slower, closer and closer to P, right? Because again, the slope, you had to have 2 points. And we're trying to find out the rate of change between 2 points. Well, between 2 points, you normally have some distance between them, and that's how we could calculate slope. But derivative doesn't have that distance between 2 points. It's, you have to imagine, right? We have the Q point right on top of the P point. So we want to know exactly at that particular point on the curve how fast something is changing, right, with respect to its slope. And it has a very similar formula to what we did in 2.7. So 2.7, we were talking about tangent lines, right? Like we had to find, this is from 2.7. We had that slope of the tangent line, right? We said, oh, M tangent is the limit as x approaches a of f of x minus f of a, and then over x minus a. So we, sit there and plug in numbers into the function they gave us, and we always had some problem, right? Because the denominator always went to 0, which made it undefined. So we had to do some kind of algebraic manipulation to get rid of that, so we could figure out what that tangent slope was. Now, what's the difference between that and the derivative formula? Well, it's nothing really. It's basically just a change of letters. We work it out the same exact way. So the derivative which we're going to call it this, okay? We're going to call it this right here. You may see it like this, like f prime of x, like that. This means first derivative, okay? Like when y'all see this little 1, that means like that's what we denote as the first derivative. If you saw, for example, you can have second and third and fourth. You can have the millionth derivative, but if you see like f prime prime of x, for example, that means like the second derivative. So this is just like a little bit of notation. And if you saw 3 little ones, it means third derivative. Another way you may also see the derivative is like this. We say y prime. That also means first derivative. So this is all just different notation that you'll see in the book or your teachers may use interchangeably. Likewise, if you see y prime prime, that just means second derivative as well. So these are just a few ways that we denote derivatives. Now coming back to this formula for the derivative, we have, instead of as x approaches a with our limit, we have the limit as h approaches 0 of f of x plus h minus f of x over h. And this is just equal to the slope of the tangent line at x comma f of x. And they're really important that the domain of f prime of x, or first derivative, is all the x, or all x in the domain of f of x where the derivative exists. I'm running out of space. So this little part right here is important, where the derivative exists. Because the derivative does not exist everywhere, okay? Kind of like we can't always find the limit at a particular value, right? Or continuity, not everywhere on a curve is a line continuous. Sometimes there's things that can cause that to not exist, right? Where it's not continuous at a certain point. So we need to talk about that for a little bit. A function is differentiable. That means we can take its derivative. Is differentiable at a if f prime of a exists. The next bit of info that's important is a function is differentiable on an open interval AB if it is differentiable at every number in the interval. And after we write the third one out, I'll draw out all this stuff on a graph so that we can see it. And it makes a lot more sense if we have a graph to look at. And then we have if f is differentiable at a, then f is also continuous. So when we say f, we're talking about the original function, not the derivative. If it was the derivative, we would have had this like f prime of something like that. But this f just means the initial function, not the first derivative function. So we notice we keep mentioning, oh, function is differentiable. We labeled or described 3 pieces of information where a function is differentiable. But there's also cases where it's not differentiable, right? So like a function is not differentiable at a if at a there is three things. It's always three things. A corner point, that's like absolute value, right? That gave us corners or v's. A discontinuity, and or some kind of vertical tangent. So let's say we just had, just a random curve, something like this. Like it really doesn't matter. I'm just making this up. And here's the point A and B right here. This is our open interval, right? Between these two values right here. We're basically investigating from here to here, all that stuff like that. So between A and B right here, looking at this curve, at every single point within A and B, we can take the derivative because the function is continuous amongst all these values between A and B right here. There are no corner points, meaning edges. There's no discontinuities. Remember, discontinuities mean like we have open circles and solid circles and a mixture of all those. And I'm going to draw a picture of these three failing right here in a second. And we also have no vertical tangents. So if you have a smooth, basically continuous curve, and you're examining some region in between, that curve where that's happening, smooth and continuous, it's differentiable, meaning we can find the derivative anywhere between x equals a all the way to x equals b. Now, what's something where it's failing these right here, where it's not differentiable? So looking at this particular uh, curve right here, graph, it's failing all three of these right here. But if we work from left to right, you can just describe what's happening. So that way, if you do see it, or you can recognize what's going on right here. So we start at x equals -8. You notice, well, we have, remember when your line begins to shoot straight up or straight down, there's something unique happening right there, right? You have, that's a vertical tangent right there. And then remember, all vertical lines have some kind of equation, right? And it's that x equals whatever that particular x value is. So we would say, oh, and x equals -8. It's kind of like a vertical asymptote, right? Remember, how do we find the vertical asymptotes from Math 130? We set the denominator equal to 0 and solve for those respective x values, and you get x equals whatever. It's the same thing right here, except that they didn't give us the equation. They gave us the curve, but to find the vertical asymptotes or vertical tangents, when you have a curve, you're just looking for where it begins to shoot straight up or straight down eventually. Now, what's going on at -2? Well, we have a discontinuity. It's not continuous because remember, in order for a curve to be continuous at a certain x value or any x value, remember one of the things that must be true, remember it was three things, right? One of them was that the limit has to be the same from both the left side and right side, right? As we approach that particular x value. In this case, that's not true, right? Because when we approach -2 from the left, your y value is up here. When you approach -2 from the right, it's down here. They don't match. That's why this is an example of it not being continuous right here. Yes, it is defined at -2 because you have a solid circle. But remember, for something to be continuous, it has to approach the same value from the same y value from both directions approaching that from the x. So you got to be approaching the same y value as you approach that x value from the left, and you have to be approaching that same y value as you approach that x value from the right. If they're different, then that's discontinuous right there. There's a discontinuity at x equals -2. And then right here we have that example of a corner point, right? Any kind of V-shaped thing. Again, if it's not smooth or continuous, right? That is an example of a corner point right there. So it's important, to be able to look at the graph like this, and then on the test, something may pop up and say, why is this thing discontinuous? Or why can we not take the derivative at x equals -2? Or why can't we take the derivative at x equals 2? You might have a multiple choice thing, right? Where it has these three possibilities right there. And you have to click, well, it's because it's a corner point. That's why we can't take the derivative at x equals 2. But let's actually find the derivative, right? Let's try that equation out. Like, let's say we have f of x equals whatever, 3x minus 1. And we want to find the first derivative, or f prime of x. And the equation of a tangent line, or of the tangent line. And I'm going to change this to 3x squared, okay? 3x squared minus 1, do that. So conceptually, what are we trying to do? A rough sketch of 3x squared minus 1, that's a parabola that's been shifted down 1, and it has some vertical stretching of 3. So it's just basically, we have a little curve that looks, something like this. And here's x equals 2. I'm just making this up. So what we're trying to find is, a line that just touches that one particular x value, right? Like that's the question mark. That's what we're looking for. That's what the tangent line is. Remember, it's just a line that only basically kisses one point of your initial curve. So how do you find the equation of any line? You always need two things, right? The slope and a point, right? Gotta have a random point. Well, they kind of gave us a point, right? They gave us half of a point. We don't have a slope. So we gotta first find that slope. So the slope is equal to, well, what are we going to do? We're going to go back to our limit problem. Remember, is the limit as h approaches 0 of f of x plus h minus f of x over h. So this, you work it out the same way that we did, the stuff from the previous section. It's just this f of x plus h. What does that mean? It just means wherever you see an x, you're going to also plug in that plus h. How would that look in this respective, or for this respective function right here? It's going to be 3, and then you're going to have x plus h squared minus 1. This is f of x plus h. Remember, whenever they say f of whatever that thing is, that's what you plug in for x. But I still got to have the 3, and I still need the minus 1. That's still also important, okay? So this whole chunk right here is just the f of x plus h. We still need the f of x part minus f of x. What is that? That's the entire original equation. And it's all divided by h. So again, when you see that x plus h, remember, if you had f of a number, what would you do with that number? Like if you had f of 10, what would you do with that 10? You'd plug it in, you plug 10 into wherever you see the x's, correct? Right here, you just have letters now. So instead of you just having a plain old x that you're going to plug in wherever you have x's up here, you're going to plug in x plus h. That's why this is jammed in there. But don't forget the rest of the equation. We still needed the 3, we still needed the squared, and we still needed the 1. And then really important, minus f of x, you have to subtract the entire original function. Make sure you put that in parentheses because you're going to have to distribute that minus sign right there. Now, if you notice, we have a problem, right? Because we were being asked to determine, oh, what's the limit as h approaches 0 of this entire thing? And of course, we have that h in the denominator. That's always going to be a problem right here because remember, dividing by 0 makes it all undefined. So you're gonna have to simplify like crazy, right? This is where the algebra comes into play, algebraic manipulation, because we need to somehow get rid of this h from the denominator. So in this case, what we should do is probably just multiply all this stuff out, right? Like let's FOIL all this, or let's FOIL this out, right? Remember, this is FOIL right here. This is not just x squared plus h squared. You need to FOIL this thing. First, outer, inner, last two, you have to expand it out, right? That's x plus h times x plus h, right? If you forgot that. Expand it out twice to remind yourself, oh yeah, I am foiling. I need to FOIL this out right here. Again, it is not just x squared plus h squared. You have to do first, outer, inner, last two. So you actually wind up with, we still have the 3, and then you have x squared plus 2hx plus h squared. This is just the FOIL part, the purple stuff. And then we still have the minus 1. Then we need to distribute this negative into that f of x. So we have minus 3x squared plus 1 all over h. So with this type of problem, finding the derivative, take your time with it because there's a lot of arithmetic that people mess up on, or they FOIL incorrectly. They don't distribute incorrectly right here. Little things like that add up. Like they'll go, oh, minus 3x squared, but they won't say plus 1. If you do that, the whole problem's going to be off right there. So take your time with this. It's not a race, all right? Write down all the steps. If you can't go from here to here instantly, that's fine. Write out the FOIL and do FOIL and write out every single term and then add them up to get to here, okay? You're not penalized for writing too much, okay? But you definitely can get stuff wrong for writing too little. All right, so we continue on, right? Because we're not done right here. What else do we need to do? Multiply this 3 out into all this stuff. So we have 3x squared plus 6hx plus 3h squared. And if you notice these ones, you can knock them out. -1 and +1. You can slash them out if you want. I still have this minus 3x squared though from here. Got to carry that. And it's still all divided by h. So from here, we still have that problem, right? Because the h is in the bottom, h is going to 0, we still get undefined. So we got to keep simplifying if possible. If you notice, well, look, the 3x squareds go. All right. So now, what are we basically left with? A bunch of terms that all have an h in them. Look at that. This is what we have left over. You notice how everything has a common factor of h right here. We can divide every single term by h. So be careful, because I know a lot of people want to do this and call it a day. No, 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 no. Do not sit there and get slash excited and do that. That's incorrect, because this bottom has to go into everything up top. So if you need to write it out twice so that you can see, oh yeah, I need to divide the h into everything up top. I'm not going to do this kind of stuff again, okay? But if you need to do it to remind yourself, I need to divide the bottom into every term up top, then do that. So it helps you out right there. So what happens? What are we left with? We're left with the limit as h approaches 0 of 6x plus 3h. Because these h's reduce to 1, this h reduces to a power of 1, and this h disappears right here. So we're left with this expression. Now, can we plug 0 in for h? Yeah, right? Because if we do, are we going to have some kind of restriction or any kind of issue that pops up? No. So you're basically left with 6x plus 3 times 0, which is 6x. Don't plug a 0 in for the x, right? Because is it saying the limit as x approaches 0? No, it's saying the limit as h approaches 0. You should have x's or a constant left over when you're finding the derivative. If you have some h thing left over right here, like if you had, plus whatever 5h or something, you did something wrong. The h's must disappear at the very last step because h is approaching 0. So if you have some h stuff left over, go back and check your work. Now, what does this 6x represent? 6x 6x is the derivative of f of x at any point on the curve. So remember, 3x squared, what do we have? 3x squared minus 1 was not a straight line at all, right? Remember, it was this 3x squared minus 1. So it was something like that. If you think about it, remember, slope was always like a nice straight line, right? Between 2 points. But this is not even a straight line right here. This is a curve. So this, what's nice about this 6x is it's telling us, oh, well, this is going to be the slope, or give us the slope, the instant slope at any point on this curve right here. But we're not finished, right? Because what were we asked for? We asked for the derivative and to find the equation of a tangent line at x equals 2, right? That's what we're looking for. So what else do we need to finish this off? So we still need m, and x1, y1, right? Because eventually we're going to plug all this stuff into the point slope formula. They want an equation at x equals 2, okay? Well, from there we can figure out all this stuff, right? So remember, this 6x, that's the derivative of this particular curve. That gives us the slope at any point on this curve. So if we want the m at x equals 2, well, we're going to find f prime of 2. So f prime of 2 is equal to 6 times 2. Where am I getting this 6 from? Because this is f prime of x right here. That's the general formula for the slope of this entire curve right here at any particular x value. So we get 12. That winds up being your slope. What about y though, right? Because we still need this y value. We have the x. We know that x is equal to 2. So to find y at x equals 2, well, let's find f of 2. Well, what is f of 2 going to be? That's going to be 3 times 2, terrible 2, squared minus 1. Where am I getting these numbers from? That's from your initial equation, right? So a lot of the times they're just going to give you the x value, but to find the y value, it's not some crazy thing. You just plug in your respective x value into the equation that they gave you, and out will pop out the y value. So again, watch the arithmetic. Don't rush, right? Please excuse my dear Aunt Sally. It's not 3 times 2 and then you square it, right? You got to square it first, then multiply. So 4 times 3 is 12, right? Minus 1 is 11. So now we know that our slope is 12, and we have the point 12 comma 11. I'm sorry, 2 comma 11. And now where do we go from here? Because we're looking for that equation, right? Point slope formula. Y minus y1 equals m times x minus x1. Let's plug all this stuff in, right? We have y minus 11 equals 12, and then x minus x1, or x minus 2. And then we simplify. We got that. And you add your 11. So we get y equals 12x minus 13. So there's your equation of the line tangent to that specific point along that curve that they wanted. They will always give you a function or a curve, and they will always give you some kind of x value if they want a tangent line. Now, sometimes the problem may just ask you to find the derivative, okay? If it says find the derivative, it's not going to be some big equation like this. You're just going to apply that limit as h approaches 0 part, that very first part that we did right there. So it is a lot of steps, right? It's very tedious. But to help out, don't speed up, right? Don't try to rush things. There's, of course, lots of places we can make mistakes. The multiplication, the distribution, this adding to both sides instead of subtracting, little things like that, that will cause you to get the whole entire problem wrong. So take your time with it right there. All right, so let's try another. Let's say this time we have f of x equals square root of x minus 4. And we want, of course, f prime of x and equation tangent to x equals 5. All right. So it's the same exact steps that we did with this problem right here. It's just we're going to have to use a little bit of different algebra to somehow deal with this, right? Because it's in a root. So let's find that derivative, right? That's f prime of x. And again, watch how you substitute these values in. This says f of x plus h. What does that mean? It means where you have an x in your x equation, you plug in x plus h instead. So what is that going to look like in this instance? Well, we're going to have the square root of x plus h minus 4. So that's f of x plus h. Okay, again, wherever the x was, you're plugging in the x plus h, but you still carry everything else. We still need the minus 4. We still need the root. That was just f of x plus h. And then moving on, the rest of the formula says minus f of x. So we need to subtract the entire original function. And it's all divided by h. Now, what can we do? Well, unfortunately, it's not like the previous problem where we could FOIL, right, and break stuff apart and do things like that. You can't sit here and break this out. You cannot say, oh, square root of 4 is 2. Remember, when stuff under the root is attached by addition and or subtraction, you can't break apart the root stuff. But we got to get rid of the root, right, somehow, because we have this 0 problem in the denominator. Well, remember, if you have roots and fractions, even if you didn't have fractions and you got to get rid of the roots, what do? You multiply by the conjugate, right? That's what we're going to have to do right here. So remember, the conjugate is just a fancy form of 1. So you just change the sign in between of those two roots in this case. Now, why did I drop the parentheses right here? Well, I did distribute the negative sign into this radical, right? That's why it's just like this. This does not become plus 4. Why? Because that's trapped inside the root. You don't distribute this negative sign into this term and this term because that's a root right there. It only applies to the root. So that this stuff still stays the same.
Mrs. Fryer, why did you put a -4 underneath the root?
Because so remember from the f of x plus h, remember initially our function was x minus 4, right? F of x plus h right here says wherever you see an x in this function, this entire function, you plug in x plus h. So I did that right here, but I still have to include the 4, right? Kind of like if they asked you, what if the problem said find f of 7, for example, how would you work this out? You would go, oh, I'm going to plug the 7 into here, right? But I can't just go square root of 7 What else do I need? I
Oh,
have to,
yeah, I got you.
yeah, you got to put the rest of the equations. That's what was happening right there. Yeah, there we go. All right, so again, this is the conjugate, or they call it complex because radicals are complex numbers. So conjugate. So remember, when you multiply by the conjugate of something, you only flip the sign of the number, or I mean, you only flip the sign between the two terms right here. So this is the only thing that changes. This minus became a plus. Everything else stayed the same. You do not flip this sign of this four right here. Okay, everything else stays the same. Oh, yeah, I need to draw this. Now, when you multiply by the conjugate, remember what's nice is you get the difference of two squares. So remember, this is just when you have a minus b times a plus b, which is what we have going on right here, you just get a squared minus b squared, like that. Where's that coming from? FOIL. So we need to FOIL it out, right? This is just FOIL, but this is just a unique case where it's a shortcut of a squared minus b squared. So this is your a, and this is your b. This is your a, and this thing here is your b. So if I go a squared, what is that? Well, what's the square root of something squared? Well, the square and the squared knock each other out. So you're left with just x plus h minus 4, because that's a squared. Take this and square it. The square root of something squared is just whatever's inside the root. So the root's gone. Then it says minus b squared. Well, b is the square root of x minus 4. If you square x minus the square root of x minus 4, again, the squareds and the root knock each other out. So you're left with minus x minus 4, just like that. Parentheses are important because there's a minus sign. So again, because the formula says minus b squared. And it doesn't matter which b you square, nor does it matter which a you square because it's the same terms. So the signs definitely matter. And it's all divided by what? Well, we have h times all this nasty looking stuff, right? There's no point in multiplying this through because it's not going to make anything any nicer. You're not going to be able to simplify stuff like what was happening in the numerator. So I'm just going to leave it in factored form. So we have, it looks so bad, right? It's just like, geez, I just want to ball up your paper and throw it away, right? It just looks disgusting right now. But if you keep going, stuff will simplify. So if you notice up top, what more can we do at the top? Well, what if we distributed up top? What happened right there? You'd see that we have x plus h minus 4 minus x plus 4, right? Got to distribute. The bottom has not changed, unfortunately. But now look at all the nice little things that happen. Look what's happening up top. The x's cancel. What else cancels? The 4s. And what are you left with? Just h up top. So even though these problems, these derivative problems are tedious, you know you're on the right track because when after you're done multiplying and doing all your little algebraic manipulations, everything up top without an h should cancel out. So again, I'm gonna say that everything without an h should cancel out up top. What canceled up top right here? The x's and the constants only. What canceled out with the last problem? Remember that 3x squared and the 1 canceled out, right? And all we were left with was h stuff up top. If you have other terms floating up top, like numbers or x's with no h's connected to them, at this point, you did something wrong, okay? There must only be h stuff after you're done multiplying things out. Why is that important? Why must we be only left with h's? Well, because that's great because now what can we do? Look, that and that can cancel. So what are we left with? We're left with the limit as h approaches 0 of 1 over the square root of x plus h minus 4 plus square root of x minus 4. Now we can plug the 0 in for h, and we're not going to get 0 in the denominator any longer. Remember, that's the whole goal with doing all this algebra junk, is to get rid of that h from the bottom somehow, because that h will always approach 0 when you're finding the derivative. That's always going to be a problem, unfortunately. But we got to do something to get rid of it. Whether it's, FOIL stuff out, multiply by the conjugate, use some trig identity, whatever, right? Now if we plug 0 in, what happens? We get 1 over square root of x plus 0 minus 4 plus square root of x minus 4. Remember, you're not plugging 0 in for x. Remember, it's the limit as h goes to 0, not x. So those x's stay. And then what are we left with right now? We have, well, we just have 1 over square root of x plus 0 minus 4 is just square root of x minus 4. Plus, you have another square root of x minus 4, right? We got 2 of those in the bottom. Can we simplify this a little further? Sure, because if you have 2 of the same things in the numerator denominator, you can combine them, right? This is 1 over 2 square root of x minus 4. And again, this is, I'm going to call it f prime of x, or I'll say it's equal to y prime. Those both mean first derivative, right? That's the derivative equation for our curve. So again, a very tedious problem, right? We're still not finished with it, but a very good checkpoint, like I mentioned before, is once you're done multiplying and algebraically manipulating all your stuff, when you cancel things, after a certain point, you should no longer have stuff with just x's or numbers. There must always, it can only be h stuff that should be left over. Just like with this, we only had h stuff left over. All your x's and constant stuff without h's need to cancel out. If not, go back and check your FOIL or all your algebra steps. So we have now our derivative function for this equation, right? But we were also asked to find the tangent line to x equals 5. So remember, what do we need? We need the slope and a point. Well, we can find the slope at x equals 5, right? Like, what do we do with the last problem? We plugged in that x value into the derivative, right? So m is equal to f prime of 5. That's 1 over 2 square root of 5 minus 4. That becomes 1 over 2 times the square root of 1, right? But what's the square root of 1? 1. 1 times 2 is 2, so you get a half. That's our m right there. Now, what about our respective y value? Well, y is equal to f of 5, right? So to remember, they gave us the function, right? That's a relation between x and y. They gave us the x value. So to find the y value, we plug this number in to the equation. If you want, you can do that step first before you even find the derivative because it's fast and easy, right? This one in this case is just the square root of 5 minus 4, which is square root of 1, which is 1, right? So we now have the point 5 comma 1. This is x and y, or x1, y1 if you want to label it like that. Now, where to go from here? Well, point slope time, right? Got this. Now, in this instance, we have y minus 1 equals a half x minus 5, right? So we simplify this. We get y minus 1 equals 1 half x minus 5 halves. And then from there, we're going to add 1, correct, to both sides. So you get y equals 1 half x, and then negative 5 halves plus 1. That's like saying negative 5 halves plus 2 halves, right? Like if you find the LCD. So you get minus 3 halves in the end, like that. So that's your equation of the line. So two parts, right? Like maybe in the homework and stuff, it'll say, oh, what's the derivative of this equation? So this would, that you would stop right there and type that answer in. Then if it asks you for the equation of the line at that point, you would stop right here. Just make sure you read the directions, okay? Because if it says just find the derivative, don't sit there and go, oh well, I didn't have an x value, I know what to do, so I just made up a number to plug in and get some equation. If it's not asking for equation, don't start making up stuff, right? Don't start making up numbers if it didn't give it to you. They will be very specific in what they want. All right, so now what I'm gonna do is I'm just gonna go back to the older sections because it's the same thing as 2.7, and I'll just throw up random problems that we can try out just to see. All right, so here we have a graph, right? Just a random graph. And we're being asked about the limit as it approaches a particular x value 2 in this case. Now saying, does the limit exist as x approaches 2 from the left, or is it going to something? Remember, you can always, it could be a finite number, it could be it does not exist. So as x approaches, the limit as x approaches 2 from the left. Well, here's 2. Remember, limits are about the journey, right? Like as you get closer to that x value, is y homing in on a particular number. And when you have one-sided limits, that's definitely possible, right? And you don't care if you have open or closed circles. It's just about what are you approaching. So as x approaches 2 from the left, we're coming from this direction. Where's your line going with respect to y? Well, it's y equals 1, right? It's going to that. That circle, whether it's open or closed, is irrelevant for this limit, this one-sided limit. Because remember, it's about the journey, like where are you going? Where are you going? Now, as we approach 2 from the right for the second one, that's us walking from this direction, 2 from the right. Where's our y value going? That's positive 3. Now this one says, what's the limit as, or it's asking, what's the limit as x approaches 2? So this is not a one-sided limit. Remember, in order for a limit to exist at a particular value, I'm not saying one-sided, I'm saying the limit itself at a particular value, the limit must be the same from both the left side and the right side, right? They both have to be homing in on the same y value from both directions, but they aren't, right? So what's that in this case? Does not exist. And you can say because b slash c, 1 does not equal 3, right? If they were both 3's right here, or both 1's, or both the same number, then yeah, the limit would be that respective number. Now, what about f of 2? Is this function defined at 2? That's what we mean by f of 2, right? Like if you could walk there, could you physically land on something, or would you just fall through a hole forever and never get there? Well, it does, right? It does exist at f of 2, or f of 2 does exist. Why? Because you have a solid circle right there. If you have a solid circle at that particular x value, it is defined for that particular x value, and it's whatever that y value is, which would be 1. Now, if these were both open circles, then it would not be defined, right? Because open circle means not included. Solid circle means included, so therefore we can say, yes, it's defined right here. Now, is the line continuous at x equals 2? Remember, there were 3 criteria that had to exist for that, right? Remember, the limit had to exist as you approach that value, which it doesn't. So it already fails that. The other one was that it had to be defined, right, at that x value. So it is defined. But then the third criteria was that the limit at that particular x value had to be the same as that defined value right here. So let's say the limit did exist, right, and it was like 5 right here. But because this is 1, the line would not be continuous at x equals 2. So the answer is no. And you can say it's because f of 2 does not equal the limit as x approaches 2. Two different things, right? You have a d and e, and you have this. 2 different values right there. They have to be the same thing. All right, so now we have an infinite limit, right, of a rational expression. Remember, when we're working these out, We can't just go, oh yeah, that's infinity up top and infinity on the bottom. That equals 1 or infinity. That's all wrong. Can't do that, right? Remember, infinity over infinity was, we call that indeterminate form, right? Because infinity is not a concrete number. It just means a really big number or a really small number, like if it was negative infinity, right? So what do we do right here? Well, remember, when you had a rational expression with infinite limits, you divided everything by the highest power of x, or the dominant term from the denominator. So we're going to divide everything here by x, right? And see what happens. And again, it's because the highest power of x from the denominator, not because they were both coincidentally x, it's because x the first is the highest power from the denominator. That's why we're dividing everything by x the first. If this was 4x squared, we would have divided everything by x squared. Now, what happens, right? Why do we do that? Well, because we can start simplifying things. This becomes 2 plus 3 over x. This is 4 minus 7 over x. But now if we plug in this infinite limit, right? If we plug that in, the infinite limit, what happens right here? This is still 2 and this is 4. But what's 3 over infinity, or negative 7 over infinity? Remember, what do we say? A constant over plus or minus infinity always goes to 0. So this is 0, 0. So we're left with 2/4. But remember, don't leave fractions in unreduced forms, right? If you can reduce anything, whether it's a fraction, a root, something, reduce it, right? So the answer here is 1/2. Do not sit there and on the test, don't put 2/4, because you'll get partial credit. Why? Because you didn't reduce the thing. Or if you had like square root of 20, that's not the final answer. It's 2/5, right? This is reduced right here because you can break this up into 4 times 5. And then out comes the square root of 4, which is 2. So stuff like that, y'all got to reduce as well. Don't put decimal answers either for roots unless the problem specifically says give a decimal round off to, 2 places. But if it doesn't, and you can reduce, like pull out a perfect square in this case, you got to do it. This is the correct answer. It's reduced right here. That's not reduced. If you forgot how to do that, that's algebra, right? You go back on Google and say how to simplify radicals if you need more practice with that. But yeah, coming back to this, the limit of this expression as x goes to infinity is 1/2. Now, what if we tried? Okay. Now, if we look at this one, this is a piecewise function, right? It's not an infinite limit, right? Because the limit it's asking about is a finite number. So how do we do that, right? If it was just one function, right? Like we just plug the number in, because if we plug 3 into either of these, there are no issues. There's no restrictions like zeros in the denominator. We can just plug it in. But this is a piecewise function, right? And they're centered around 3. So remember, to find the limit, what do we need to find, or what do we need to see? We need to ask ourselves, does the limit as x approaches 3 from the left of f of x equal the limit as x approaches 3 from the right of f of x? Big old question mark, right? Remember, when we first talked about limits, what did we do? We made a t-table, right? And we chose values a little smaller than that x value. and one's a little larger than that x value, and we want to see if their y values were homing in on the same thing, right? Or going to the same thing, same value. This is the same case, right? But instead of us making a t-table, we're going to plug 3 into both of these equations, right? And we just want to see, do we get the same y value? It's just yes or no. If yes, what is it? If not, then we say the limit doesn't exist. So 3 from the left means we have to use this one, right? Because this domain restriction says x less than 3. So we have 2 times 3 plus 1. Is that equal to? And then from the right, we would use the second part of the piecewise function. So 3 times 2 minus 5. I'm sorry, 3 times 3. So we get 6 plus 1 is 7. Does 7 equal 3 times 3 is 9 minus 5 is 4? Is that true right there? That's false, obviously. So the limit does not exist. If they're both the same number, right? Like if they both popped out to 7, then the limit would be 7, right? That's what we would say right there. But in this case, the limit does not exist. What about the limit as x approaches 3 of 4x minus 12 over the absolute value of x minus 3? Remember with absolute value, they were a little tricky, right? First, we had this issue that we can't plug 3 in because we get you actually get 0 over 0 right here, which is undefined, but it's because you have a 0 in the denominator, so that's the problem. And the second problem is that it's absolute value. Remember, with absolute value, you had to break apart the limit into two things, right? Into a piecewise function. And the trick was if you had the absolute value of stuff, right? I wrote like a generic formula for that. You said, oh, you would have stuff, we would just drop the bars, and it would be x greater than or equal to the limit. That's the number that we were looking at. In this case, it would be 3. Remember, you just drop the bars. Nothing changes in the problem, right? At all. You just drop the bars and then evaluate it like that. And then we have the next one was you'd have negative and then stuff. And then that was for x is less than the limit. So with this stuff, we're only talking about the stuff inside the absolute value. Like this 4x minus 12 in this case, it's never going to change no matter which one we're looking at, because that was not inside the absolute value. Everything else outside the absolute value always stays the same when you break it apart. So if we rewrite this, we're going to have basically 4x minus 12 over x minus 3 if x is greater than or equal to 3. So notice I just dropped the bars, right? Because that's the stuff right here, just x minus 3. Nothing else changes. And then for the if x is less than 3, the top is still 4x minus 12. Remember, everything outside the absolute value stays the same. You don't care. Don't change any of it. But we are going to flip the stuff that was inside the absolute value because it said negative of the stuff. That's going to be negative and then x minus 3, like that.
So,
Yes, go ahead.
so would it be x negative x minus 3, or would it be negative 4x minus 12 over x minus 3?
Well, yeah, the thing is, right, you could do that any of those ways that you said is technically correct. Like you could say this, we could distribute this negative and say negative x plus 3. We could do that. Or we could even say negative 4x plus 12 over x minus 3. Both ways, you'll still get the same answer ultimately in the end. So you do whichever way that you're comfortable with. It's just that whichever way you do it, make sure you apply the negative correctly. Like, don't just apply the negative to the x right here and forget to multiply into that 3. Or say, oh, this is negative 4x, and not divide the negative into the 12 as well, right? Because if you're off by a sign, the whole thing just will be incorrect. So, what are we doing, right? We're looking at limits, right? We're asking ourselves, does the limit as x approaches 3 from the right of 4x minus 12 over x minus 3 equal the limit as x approaches 3 from the left of 4x minus 12 over negative and then x minus 3. So remember, the limit exists at a, we were asked about this, right? What is the limit as x approaches 3? We weren't asked about a one-sided limit. And since we're dealing with absolute value, we had to break it apart into two pieces, right? So that's why we have approaching 3 from the right and 3 from the left. But remember, the equations will slightly change whether you're approaching it from the right or the left. That's why I have to set up like this. So let's see what happens, right? Are we going to get the same values right here? If you notice, if I plug 3 into both of them still, like 3 into here, I still get 0 on the bottom. 3 into here, we still get 0 on the bottom. So remember when we had those issues, what do we have to try to do? Oh, let's try to manipulate this thing algebraically to get rid of the issue. And guess what? You can, right? There is something we can do to both of them. Or if you have no idea where to start, I mentioned it before, and you got to simplify a rational expression. Ask yourself, can you factor something? Can we pull out a GCF at all? Question, Janera?
That was from earlier. Sorry.
Oh, all right, so what can we do right here? There's a GCF, right? Look at your numerator. At both of them, what do they both share in common? A 4. So what if we pull out a 4? What are we left with? X minus 3. And we can do that same manipulation to the right side. Does that help out? We still can't plug 3 in because we get 0, but what happens? That reduces, that reduces. Huh. So what are we left with? We're left with 4 equals 4 over negative 1 if you really want to do that, because that negative right there. But ultimately, what does that conclude? We get, does 4 equal a negative 4? No, that's false. So because we got two different numbers, right? That tells us that the limit does not exist. So
Can you move the board up?
wait, what now?
Can you move the board up?
Oh, sorry, yeah. So your ultimate answer is that the limit does not exist. Because you can see we got two different values right there. That won't always be the case for all absolute value problems, right? So don't always expect, oh yeah, it's going to be, we're going to get opposites all the time. No, you can get the same numbers, right? It just depends on the equation. All right, let's see. All right, so we have the limit as x approaches negative infinity of 6x to the fifth plus 3x cubed minus 5x over 3x cubed plus 2x squared minus 2. And of course, if you plug in negative infinity, you're still going to wind up with some version of infinity over negative infinity or something, infinity over infinity. It doesn't matter if either of them are positive or negative. That's indeterminate. So what do we need to do? Well, remember, we have a rational expression, right? You divide everything by the dominant term from the denominator. So in this case, this is the dominant term, x cubed. So you're going to divide everything here by x cubed.
Why are we dividing by x cubed again?
Because when that's the dominant term from the denominator, and as far as the behavior of graphs behave, what determines overall how a graph will behave is the most powerful piece in the denominator. So this x cubed is the most powerful piece, right? Because it's higher than x squared and higher than this one, which is x to 0. So that's the rule for rational expressions. When finding infinite limits, you always divide by the highest powered x in the bottom part of your fraction. All right, so let's start simplifying, right? Reducing, like, well, we could see, oh, this goes completely away, this goes completely away. Some of these partially will reduce, right? I say partially because, like, 6x to the fifth over x cubed, you're still left with 6x squared, right? We still have an x squared because x to the fifth over x cubed is x squared. This is plus 1. Remember, it doesn't reduce to nothing. It reduces to 1, or 1 times 3, which is 3. And then we have minus 5 over x squared. This is x to the first, correct? So you're left with 2 x's on the bottom. Now, in the denominator, we have 3 plus, and then 2 over x, because you have 2 up top, 3 on the bottom, so you're left with 1 on the bottom. And then with this one, nothing cancels out at all. So now if we plug in negative infinity in, would you still be left with some form of infinity over infinity? No, you would not be, right? Why? Because if I plug negative infinity to the bottom, for example, this is still 3, because there's no longer an x being multiplied with it. Remember, a constant over infinity or negative infinity, like what's happening right here, in both these cases, that goes to 0. So that's 0 minus 0. Really doesn't matter. Up top, what do you have? Well, you can plug in. What if we did that, right? Like that, plus 3. 3 doesn't change. This goes to 0, right? Constant over infinity or negative infinity is just 0. So what happens right here? Well, I mean, you have 3 on the bottom, but who cares? What we really care about is what's happening with this negative infinity squared, right? Well, if you take a negative times a negative, right, you get a positive. So now if I take a positive number, a really big one, and I multiply it times itself, I get an even bigger number. Times a constant, it's still big, right? Plus another little constant, it's still infinity. Right here, we don't have infinity over infinity, so we're okay, right? This just goes to infinity. This is your answer right here. Remember, the reason why we were able to keep infinity up here and say, oh, 1 to infinity, and we didn't have to do further manipulation algebraically is because you were just left with one infinity. All right. It's just that when you have infinity over infinity, that you have to start doing stuff like divide everything by the dominant term in the denominator. If my answer was 3/infinity in the end, like this, right? Like if you had whatever 5/infinity and you worked out one of these problems, that'd be 0, right? Because that's what's been That's what happened here and here. Like 2/infinity or negative infinity is still 0. This goes to 0. This goes to 0. But if in the end you have some variation of a constant over infinity, that just goes to 0. So that would be your limit in that case. All right, let's see here. All right, we'll do one more. All right, so we have this piecewise function right here. It's not asking us to find the limit. It's asking us why is this discontinuous at x equals -2. So we already know it's the limit, or it's discontinuous at that value. They want to know why. Why specifically? So remember, something is continuous if, and remember there are 3 conditions, right? It was the limit as x approaches, it'd be -2 of f of x exists. The next one was what? Is f of -2 defined? And the third condition was, does the limit as x approaches -2 of f of x equal f of -2, right? They had to be equal right there. So it's failing one of these, right? Why? At least because why? It's saying why is it asking why is it discontinuous? It's not going to ask us why it's discontinuous and it turns out to be continuous. So it's one of these is not working out and we just need to figure out which one is it. All right, so how do we do that, right? Well, it doesn't matter in which order that you actually work these out. So let's start with B, for example. It says, is f of -2 defined? Well, yeah, it is, right? It says, oh, when x is -2, y is equal to 3. When they say defined, they mean you have, like you would have a solid circle at that value. So if we had -2 right here and we have y equals 3, we know we have a solid circle. That's an example of what's going on right here. So this is defined right here. So this one checks out. Oh, this is x plus 2. I was wondering why. I was like, what the hell? Put x plus 2 right here. Change that. That needs to be plus. You got to put x plus 2. X plus 2, x plus 2. So now, how about part A? It says continuous if the limit as x approaches -2. Does that exist? So that means we're looking at this equation right here, right? So, because again, we have to examine the limit of this thing. Does it exist right there? So how do we go about doing that? So you may be thinking, well, why is it that we're finding the limit of this thing when this says x cannot equal 2? Remember, limit's about the journey. It's about you getting or approaching that number. It's not about equaling, right? So that's why we're able to do this right here. This means as we get closer to -2. So as we get closer to -2, though, we see we have a problem. What is it? You get 0 in the denominator. That happens like 99% of the time when you have fractions, right? That number that you're examining the limit of as you get closer to x, that particular x value, it's going to make the denominator go to 0, like 99% of the time. So you're going to have to do some manipulation, right? Well, what can we do? Remember, you have no idea where to start. Ask yourself, can you factor? You sure can. Factor that top. That top becomes x plus 2 times x minus 3. Well, look at that. The x plus 2's go. So now we're left with the limit as x approaches -2 of x minus 3. Now can we plug in -2 into this? Sure can. This is -2 minus 3, and we get -5. Well, so we know now the limit as x approaches -2 of f of x is equal to -5. So the first condition checked off, right? Like we had A, B, C. We checked off B already because it's defined. A is checked off. But what about condition C? Remember, condition C was, does the limit as x approaches -2 of f of x equal f of 2, right? That was the question. Or, I'm sorry, -2. So we're being asked, is that a true statement, right? Is that a true statement right here? Well, it isn't, right? Because what was the limit as x approaches -2? We got -5. Does that equal f of -2? What was f of -2? That was 3, right? That was the other little chunk of the piecewise function they gave us. This is obviously false. So this is why it's discontinuous at x equals -2. So if like a problem pops up like this on the test, you know, it'll have these three options that you can choose from and say, why is this thing discontinuous? Was it because it's not satisfying the condition from C? Or maybe A, the limit doesn't exist, or maybe B, it's not defined, right? It just depends on what your equation is and what the value is that you are examining.
Would it be true to say that the limit does not exist as well?
No, the limit does exist because we got -5, correct? We got -5 right there.
Right, from that part of the piecewise function.
Right. The limit does exist. It's -5. Basically, what's happening here is if we drew like a rough sketch of what's going on, like we have here's -2. What's happening here is, and I'll just put -5. right here. This is -5. What's happening is your graph is doing basically something like this. And then at f of -2, we actually have 3. This is what your graph is doing right here. You see, so as I approach -2 from both the left side and the right side, it's approaching the same y value, and it does exist. But is it defined? And it's also defined at -2 because we have a solid circle. But is it continuous at -2? No, it's because in order for that to be true, this solid circle would have to be right on top of this this open circle right here. So you are right, the limit does exist, but it's not continuous, right? Continuity and limits are two different things. In order for something to be continuous, the limit has to exist, right? It's like limits are a subset of, like, if you had a house, right? The house would be the continuity, and limit existing would be one of the family members that lives inside, like that. But does that answer your question,
Yeah, I'm good. I understand.
Shanera?
Is it possible for you to do some examples with trig? Because some of the homework problems have trig on them, finding the limits of trig functions, and I don't know what I'm doing.
Well, do you have the example?
I can pull it up. Give me a second.
Yeah. I bet you like whatever trig cosine or sine of e to the x or whatever. I actually did one like that on the lecture. But yeah, go ahead. What is it? Like the limit.
Okay, so one of the problems was as the limit of x approaches infinity,
Right.
in the parentheses, you have e to the negative x plus 9, and then the cosine, parentheses, 7x,
Right. Yeah.
in parentheses. That's the problem.
Yeah. 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 So remember, if you have negative exponents, you need to make them positive. So this e to the negative x, this e to the negative x becomes 1 over e to the x, right? Because we're just flipping and making positive. This cosine is still there. It doesn't change. It's still the same thing. Now remember, e is a constant. E is equal to about 2.71. So if we have 1 over 2.71 to the infinity, that just goes to 1 over infinity, which is 0 right there. Now what's happening with the 9 cosine of 7x? Remember, cosine and sine are sinusoidal. They're wave functions. They just bounce, right? Remember we looked at the graph of sine from a previous lecture. Cosine does the same thing. It's just slightly shifted, but it does this right here. This is cosine of x. These constants don't affect the behavior of it. It still oscillates between 1 and -1. In our case right here, we would say it oscillates between 9 and -9 because that's the amplitude, but that's not going to affect the overall limit. So remember, we're asking as x goes out to infinity, where's our y value going? So we know that this piece is approaching 0, but looking at the trig function, if we were to go out to x equals infinity or just keep going forever to the right, does it look like our y value is going to land right on top of one number? No, because what is it doing? It's bouncing forever between between 9 and -9 in this case. If it's always bouncing, which sine and cosine will always bounce between something, it's never going to go to one specific y value. Like this goes to one specific y value, it's 0. This never will. This just oscillates between -9 and 9. So that limit doesn't exist. The limit's never going to exist for a sine or a cosine problem. And it doesn't matter how many numbers or what you have in here, because again, it's still going to be a wavy thing. Wavy things will never, this is never going to hone in on one specific y value right here. So if you have 0 plus a d and e, what's that ultimately going to be? Just d and e, like that. So that's what's happening right there.
Okay, I have another example too. It's an arctan problem.
Yeah, it's the same thing, right? That's the same one that I did in class. It doesn't matter. What was it? Arctan of what? Limit as x goes to infinity of what? Arctan of what?
E to the x.
Yeah, it's the same thing. Like, again, what's the graph of arctan of x look like? What does that do? Remember how I said when we went over this in the lecture, I said you need to remember this function because it comes up 50 million times. But it doesn't matter what's inside because guess what? It will still do this. It's still always going to do that. And if you don't remember these graphs like cosine, sine, tangent, arc, all that stuff, then yeah, you should go back and look at the notes that was posted on Canvas. Paul's online notes, he has a wonderful trig review. Look at all that stuff because you have to know that right there. Because once you do, these problems aren't difficult at all because the trick to doing this arctan and this one was realizing, oh yeah, I remember what the graphs look like. This arctan will always look like this. Don't freak out and go, well, now there's an e to the x in there, or there's some other weird thing. What's it doing? It's still doing the same thing. Just like cosine and sine will always be this wave thing no matter what's inside of here. So with this arctan, it was very unique because it wasn't a d and e. It didn't oscillate. It was trapped between two y values. Remember, I drew this out on that lecture. This is pi over 2 and negative pi over 2, like that. So the limit as x approaches infinity of arctan of whatever, I say whatever because this could be anything, is still pi over 2. And that was it. Now if they said, okay, what's the limit as x approaches negative infinity of arctan of e to the x, guess what? It's the same concept. What happens if you keep walking to the left? There's a horizontal asymptote right here of y equals negative pi over 2. So the trick with the trig ones is just you got to know what the functions look like. And that just comes down to, you know, memorizing them. Or you just practice, right? Like you'd say, okay, what's the, get a sheet of scratch paper, write sine, cosine, tangent, and just keep drawing the sketches until you commit them to memory. And the arctan one for sure, because this comes up a lot in Calc 2 all the time. So yeah. It just comes down to memorizing shapes. Yeah.
Quick question on this e to the x. There's a
Right.
homework problem that says you got to put e to the first power, and that anything by one, its first power, it's itself, right? So it'd be 2.71.
Yeah, but you're not going to put it as a decimal. You just leave it as e, right?
Well, the answer when you enter, I'm just trying to enter it in there to get the correct answer, but it won't accept anything. 2.71, 2.72.
Which problem is it?
It's number 4 on 2.5.
All right, let me see. I'm looking right now.
And these problems that I just gave came from 2.8 homework.
So what was that E1, the 2 point, what was the
No,
section?
number 4, 2.5.
Okay. So you're saying you're entering, so it's the piecewise function, right?
Correct. The bottom limit is 1, right? 1 squared is 1, so it took that. So, But if you put e to the first, put the one as the x at the top, right?
Hold on. Let me write the prompt down because I think I know what's going on right here. So you have f of x equals, and then it's a piecewise, and you have e to the x if x is less than 0, something like that, and then x squared if x is greater than or equal to 0, you have that. And then a equals 0, is that your thing?
No, it's 1. Everything you just wrote down is perfect, but the 1. Yeah.
1, and then 1 like that.
Yes.
That's what you have. And it's saying the limit as x approaches 1 from the left, correct for you?
Correct.
And then 1 from the right. So yeah, for this one right here, 1 from the left, it would be of f of x, it would just be e, like that. That's what it would be. Why? Because you have to plug in, if it's saying 1 from the left, you're using the leftmost, or the equation where the domain restriction is to the left. So you would say, oh, it's e. And then for this one, it would just be positive 1 because you're going basically 1 squared, which is 1, like that. So your answer should be e and 1.
So I shouldn't put 2.7. I should just put
No, e, because 2.7. But the thing is, if you say 2.7, you're saying that's equal to e. Is that true? No, that's false. And the thing is, when I say, oh, e is equal to 2.71 like that, that's just an approximation. If you actually type into your calculator, you get something with 50 million decimals after this right here. This never ends right here. So you can't put 2.71. You have to leave it in exact form, which is e right there. That's what's probably going on right there. E or e to the first, like that. Yeah, don't ever put decimal approximations unless it specifically asks for it. Same thing with like pi. You leave it in terms of pi, like the way you get pi on Web of Science, you type, pi for pi, like that.
I understand. If it was e to the 0, we know that it's 0.
And no, e to the 0 is 1. Remember,
Correct.
anything raised
I'm
to the
sorry,
0 power
correct.
is 1, right?
Yeah.
Yeah. So remember, don't just study this stuff, right? Like this little thing that I wrote right here, this and stuff that we did after the 2.8 or whatever. Don't just say, oh yeah, I did that. That's good enough. That's all I need to learn. No, go back and look at everything, right? Look at all the problems and the homework and all that stuff. Any of that stuff can appear on the test. Don't try to guess which ones, right? Again, don't think bare minimum. What's the bare minimum you need in order to pass, right? It's okay to work more problems. More problems means you get more comfortable with this and you get stronger with it. Okay. Anything else right now? Remember, I do have the office hours, right? And like I am online an hour before this class. So if you guys, need help, go to the files tab on Canvas. I have my office hours thing. There's a direct link posted to my Zoom room. It's not on the Zoom tab. You have to go to the pages tab. I'm sorry, the files tab, and you'll see my office hour PDF that you can download right there. And you can click the link or copy into your web browser, and it'll link you straight to my room. Okay, but if you're having problems with it, send me an email. Okay, like I said, I'm there an hour before this class on Wednesday. I even have office hours on Tuesday as well. If you have questions, I'll be on the Zoom stuff waiting for y'all. Okay. So if there's no further questions, we are finished. And the Zoom, this recording, it will appear, later on tonight after Zoom uploads it to its little cloud. Okay. So y'all take care.